Good morning, guys. Today we're going to start our unit on confidence intervals. Confidence intervals are really just a tool that help us estimate what's going on in a population based on what we saw within a single sample. So let's look at our prompt for today. 10 years ago, the average height of an RHS student was 64 inches with a standard deviation of 9 inches. This year, we took a simple random sample of 36 RHS students and found that their average height is 66 inches. Does this provide enough evidence to suggest that RHS students are taller now than they were 10 years ago? So we see in the sample, we're 2 inches taller than what we saw in our population 10 years ago, but is this one sample a good enough picture, or going to give us a representative enough picture to say that, yeah, Riverdale students are taller? So we need to take this and estimate what's going on in the population. Well, if we are going to make an estimate, we're going to need, or an estimation, we're going to need a point estimator and a point estimate. Well, what is a point estimator? A point estimator is just a statistic that estimates a parameter. A statistic, something we gather from a sample that estimates a parameter. So it really gets into those unbiased estimators we talked about before. So in this problem, what statistic are we using? Well, what we're using is the sample average height. So our sample mean height is going to be the estimator for what's going on in the population. So we're going to build a confidence interval around sample mean height. Well, what's point estimate? Point estimate is just the value of that statistic. Well, what was the value of our sample mean height? 66 inches. So if I can build a confidence interval, and we'll talk about what that specifically is here in a second, if I can build a confidence interval around this 66 inches from our sample, then that should give us a good idea of how our current population relates to this past population, that 64-inch population. So let's move over and talk about what a confidence interval is. So what is a confidence interval? A confidence interval is an interval of plausible estimates of a population parameter. So instead of just saying we have one sample and then this is the number, we hope it matches up what's going on in the population, we actually take that sample and we build an interval around that sample and say, well, if this is what happens in the sample, then we can reasonably expect somewhere in this interval to be what's actually going on in the population. So that's what we mean by a plausible estimate of the plausible estimates of the population parameter. So any number, any value within that interval could reasonably be what the true parameter, the true measure of the population is. So how do we build something like that? So a confidence interval starts with a point estimate, and we're going to plus or minus a critical value times the standard deviation of the statistic. Well, point estimate plus or minus some amount, well, that actually should sound kind of familiar because you guys have seen confidence intervals before. Whenever you see any type of survey done and they say that this is the value we got plus or minus 3% or plus or minus 10% or plus or minus 1%. That plus or minus 1% is saying, well, it could be a 1% more or 1% less. That is an actual confidence interval. And we actually call that plus or minus the margin of error. Margin of error is saying that, well, we got this from our sample, but we could be off in either direction this amount. The way we calculate that is with that critical value times standard deviation of the statistic. Standard deviation of statistic, that should be familiar to us because we've been talking about that for the last few lessons. That's just the spread of your sampling distribution. From one random sample to the next random sample, how much variability do we expect? Point estimate should be familiar to us. So if we're going through, we want to actually calculate a confidence interval. So we've got a confidence interval. A lot of times you'll see that abbreviated CI, and then there's some type of confidence level. We're going to come back and talk about confidence level here in a second. So it's some type of confidence interval at a specific confidence level, and it's just taking your point estimate, or which would be whatever we got for our X bar, plus or minus this critical value. What is critical value? Critical value is the number of standard deviations necessary to capture a specific confidence level. There's that word confidence level again. Number of standard deviations necessary to capture a specific confidence level. And then we're going to multiply that by standard deviation of the statistic. So that's just what we've worked with before. Standard deviation of X bar, which we know to be standard deviation of the population over square root of n, or we could use standard deviation of p hat, which we know to be square root of p times 1 minus p over n. Those are the standard deviations we're going to work with. Now, we work with more than x bar and p hat. We could be working with standard deviation of the population, or sorry, sample standard deviation, or correlation coefficient of the sample. But for what we've done at this point, we know means, we know proportions. We'll get to the other things later. So we're going to focus on means and proportions in this unit. So we start building this confidence interval. It starts with our point estimate. So the point estimate we used was the sample mean of 66. Now we need to plus or minus a critical value. What the heck is a critical value? So remember, number of standard deviations necessary to capture a specific confidence level. So let's step over here and see what a confidence level is. So here's a confidence level. Confidence level is nothing more than the success rate of choosing same size samples that actually capture the population parameter. The success rate of choosing same size samples that actually capture the population parameter. So if I do the same sample again and again, and I build the same confidence interval, same margin of error, so to speak, how many of all of those intervals off of all possible samples would actually capture, would actually contain what's really going on in the population? That's what a confidence level is. It's kind of get a visual aid for that. So in this right here, I have my sampling distribution. Let's say that we have sample size was 36, so it's larger than 30, so we've met the large sample condition. So we know the sampling distribution should be approximately normal. So we've got really a number line of all possible sample means, all possible x bars. And we know the center of that distribution should be what's actually going on in the population parameter. So I've got all these possible x's, or x bars. And I just kind of grabbed a few of them. They're really down here on the number line, but I'm just stacking them up here in space so we kind of see how they all relate to each other. So if I was going to make a confidence interval around these, it would have a certain width to it, right? That certain margin of error. It'd be a little bit smaller, a little bit bigger, a little bit smaller, a little bit bigger. But with a confidence level, it's the exact same confidence interval every single time, or same margin of error every time. Why is it the same margin of error every time? Well, it's the same margin of error every time because you have the exact same standard deviation of the statistic. That has nothing to do with, that's based off of population and sample size. So it has nothing to do with what our actual sample produced. So if we do all populations, or all samples of the exact same size, and they'll work from the same population, they should have the same standard deviation, no matter what our sample results were. And if we're looking for the same success rate in all of them, then you should get that same margin of error. So I should get the same width on my sampling distribution, or on my confidence interval. So let's take a couple of confidence intervals. So let's say that I had this confidence interval right here. So if I center it at my mean, see how if my list of possible values, so anywhere in this interval based off my sample could be what's really going on in the population. This specific confidence interval captures my parameter, captures what's really happening in the population. Well, so does this one and this one. All of these happen to capture what's going on in the population, or what's actually occurring in the population. But a different confidence interval, a smaller confidence interval with a smaller margin of error, would not always capture. These first few actually capture what's happening in me, but out here, that one doesn't capture it. This one over here doesn't capture. So these more extreme means don't capture what's really going on in the population. So that's what I mean by confidence level. Confidence level is how big, more or less, do I need to make this interval? All right, so how many standard deviations do I have to go in either direction to make this interval in order to actually capture what's going on in the population? Now, I've stacked all these up here in space. Realistically, all these values are sitting down here. So we could do this exact same practice down here on the x-axis. So if we'll notice, I could go all the way, I could use any mean. Remember, this is all possible mean. I could use any mean all the way out to about here before we've excluded what's going on in the population. Same thing here, I could go all the way over here. So all of the means between here, here, here are still capturing this middle value until I get out to about here. So what we notice is that if these are my standard deviations, that's 2 standard deviations. So that means that any mean between this value and this value within 2 standard deviations would actually produce a confidence interval that would capture what's going on in the true population. Well, we've worked with this before. The fact that we are using normal distributions is because we know that within 2 standard deviations, how much of our data, or in this case, how many of our samples are actually within 2 standard deviations. Well, we remember from our normal distribution work that that's 95%. So 95% of the area is covered in here. So that would actually produce a 95% confidence level. So if I was going to go 2 standard deviations, if I wanted something this big, I would need to use 95% confidence level. Now, if I used a smaller confidence or smaller interval, then I need to have less confidence that I'm going to catch what's going on. So this one actually fits all the way between 1 and -1 standard deviations. So this was representative of a 68% confidence level because it only 68% of its means can capture what's going on in the population. So that's what I mean by a confidence level. It means if we take many, many samples of the same size, so in this case 36, from this population, these Riverdale students, and we're going to focus on, I want 95% confidence. All right, so about 95% of all samples. So 95% of all sample means, so that's 95% of all samples, result in an interval that captures the true mean height of all 2020 RHS students. The true mean height of all RHS students. So I need to have a large confidence interval to capture more values. So now that we've kind of have an idea of what we mean with a confidence level, we'll work more on that, try to refine that idea. Let's step back over and use this 95% confidence level and then figure out what the actual interval for our, say, 66. So say that this was our 66 right here. What are these actual 2 boundaries of that confidence interval? So let's slide back over and look at that. So let's actually use this 95% confidence. So we're going to use confidence level of 95%. We just saw that's going to give us a nice wide interval, give us a really good chance of capturing what's really going on in that population. So how do I get the critical value? How do I get the number of standard deviations that would block off a 95% confidence level? This is just going back to what we did back with our normal distributions, and that's why we like normal sampling distributions. To get a 95% confidence level, I would have to go within 2 standard deviations of the mean. That's the plus or minus 2 standard deviations. That's all that's telling us. Plus or minus 2 standard deviations. If I wanted to use that 68% confidence level, I would use plus or minus 1 standard deviation. So my critical value would be a 1. If I was going to use, say, 99.7 confidence level, then I would use plus or minus 3 standard deviations. So it ties right back into the 3 sigma rule, or the 68, 95, 99.7 rule that we talked about way back early in the course. Now, we don't always have to use one of those numbers. I could use 90% confidence level. It's a very common confidence level to use. And in that case, I would just use an inverse norm feature on the calculator to be able to figure out what's the z-score, because that's all these are. What's the z-score that would correspond to that middle 80% or middle 90% rather of the data. So that's what we're doing. Pick your confidence level, and confidence level really is something that you choose. How confident do I want to be? Pick your confidence level, find the corresponding z-score. So it is corresponding z-score. And then just move on. All right, now we want to get our standard deviation of our statistics, or our standard deviation of our sample mean. So we're going to use this guy right here. So we used sample mean, which was 66. We use 95% confidence level, which has a z-score of 2, and then we're going to use our sample standard deviation for sample means, or standard deviation for sample means. So population standard deviation was 9, standard deviation, square root of the sample, which was 36. So you get 9 over 3, 6, so 9 over 6, which gives you 3 halves. And we can actually build our confidence interval from there. So our confidence interval, and a lot of times you'll see me write it like this, 95% confidence interval is going to be equal to 66 plus or minus 2 times 9 halves, 3 halves, which is going to give us 3. So we might say that this one is 66 with a margin of error of 3 inches. So the sample came out at 66 inches, but we know what's really going on in the population could be 3 inches bigger, 3 inches smaller than that. So this is our confidence interval. Often you'll see it written like in parentheses, 63 to 69. So you can see it presented either way. I like it like this because it gives me an idea of what the margin of error is, so I can kind of work some stuff backwards without having to find the midpoint, figure out the difference to get the margin of error. This one's not bad because the numbers are clean, but we'll get some that are very not clean as we go forward. So let's go through and actually interpret what this 63 to 69 means. So here's how we interpret confidence intervals. We are confidence level, we are 95% confident that the interval from 63 to 69 inches captures the true mean height of all 2020 RHS students. That's all it means. We're 95% confident that the actual height of RHS students is somewhere between 63 and 69. That's what it's going to tell us. That's how we're going to use it. Now, what we want to do is figure out, what does this tell us about how we've changed from 2010 up to 2020? So let's go over and look at what our conclusion, what that final answer ends up being. So let's answer the question that was posed at the very beginning. Is there enough evidence to support the claim that RHS students are taller now than they were 10 years ago? Is there enough? And enough being key right there. Because it's statistics, we never learn anything definitive. This is what happened, this isn't what happened. We're just trying to build evidence to kind of support an idea. So let's compare what we know. We know that the mean height back in 2010 was 64 inches. We know that the 95% confidence interval for 2020 was from 63 to 69 inches. So when we want to know, is there evidence that they're taller now, we want to know, are they different? Different in the higher direction, but we've got to answer, are they different first? So if we have a confidence interval that says that realistically, right now, students are anywhere between 63 and 69 inches tall. We're 95% confident that they're somewhere between 63 and 69 inches tall on average. Well, if they were 64 inches tall back in 2010, are they different now? Is this evidence that they may be different now? Now, the answer to that, I'm going to say is no. Why is it no? It's no because if this is my list of plausible current heights, well, the past height is within that list of plausible current heights. So they could realistically still be 64 on average, and we just got a little bit taller than average sample. So that's how we're going to answer that. So if we go through an answer, we want to answer kind of with this phrase. Since the 95% confidence interval captures, the 2010 mean height of 64 inches, we do not have evidence to suggest that RHS students are taller now than in 2010. So that's the way you're going to always interpret these answer these questions about sampling and estimating for confidence intervals. You really want to know, is my target value, is it captured by my population or by confidence interval, or is it not captured? Does the entire interval exceed? Is the entire interval smaller than the value? So that's how you're going to interpret that. Now, sometimes we may want it within the interval, sometimes we may not want it within the interval. It's all going to depend on the context of the problem, but it's really just comes down to comparing where this falls relative to where those boundary values fall. All right, so that's really it for confidence intervals. A confidence interval, and every confidence interval we do is going to be built the same way. Now, the mechanics from how we build a confidence interval may be different from one to the next, but the structure is always the same. It's always point estimate, what we got from the sample, plus or minus the margin of error, which is built off of some critical value times the standard deviation of the statistic. And the critical value is always going to be how many standard deviations before we capture this interval. Now, it's not always going to be z-scores because we're not always going to be working with normal distributions, and that's what changes. Okay, so the process is the same, critical value times standard deviation of statistic. It's how we calculate those critical values and how we calculate those standard deviation of statistics that change how we make different confidence intervals for different point estimates and point estimating. But that's it on kind of a general outline for confidence intervals, and I will see you guys in class tomorrow.